microfarad capacitor. To solve this, we want to find which of these capacitors are in series and which are in parallel. Here we see that these two are in series, these two are in series, however these two are also in parallel. So to find this series right here, we'll need to find this parallel first, and then we can see these three right here are all in parallel. So to simplify the problem, we're going to want to sketch in little dots that show this relationship. So we see these two are in series, these two are in series, and these two are in parallel. So to begin solving, we are going to want to know what equations we need to use to find these series relationships and parallel relationships. The equations we will be using are for capacitors in series and capacitors in parallel. For capacitors in series, we have 1 over the capacitor equivalent is equal to 1 over C1 plus C1 over C2 plus however many more capacitors you have. So this 1 over Cn and this 1 over C times n minus 1 is the ending of the equation. So let's say we had 7 capacitors in our series equation total. This would be C7, and this n would be 7, so it's C7 minus 1, so C6. So it just keeps going until you're out of those parallels, or capacitors in series. So here, as you can see, we only have 2, so this is C1, and this would be C2. Here, it's only 2, so C1, C2. For parallel, it's very similar. We have the capacitor equivalent is equal to C1 plus C2, and then it keeps going just like the series equation for each. So if we had 4 total in parallel, this would be C4, this would be C4 minus 1, so it's C3. So it's C1 plus C2 plus C3 plus C4. To begin solving this combination of capacitors, we want to begin with the series on the left. So we have our equation now lined out, and now we have these two blocked off, and this is our first series. So to solve this series, we have 1 over the capacitor equivalent is equal to 1 over 6.0 microfarad plus 1 over 5.5 microfarad. And this will give us our intended goal of giving us what this series is equal to. So once we use this equation, we find that the series is equal to 2.86 microfarads. Here, now that we have this, we are going to want to remember this number, and this will be one of the numbers we use in our final parallel calculation to find the total. Next, we are going to want to find this parallel right here, the 1.75 microfarad and the 25 microfarad. To do that, we have our equation pulled up, and we have these two blocked off. For the parallel on this bottom right, we have the capacitance equivalent is equal to 1.75 microfarad plus 25 microfarad equals 26.75 microfarad. Once again, we are going to want to remember that number, and that will be our C3 in our parallel equation for the final number. Now that we have this 26.75 microfarad, we can take out these two numbers and fit in that 26.75 right here because they were in parallel. And now this will be the number we'll use along with this 2.5 to find this series on the right-hand side. So for the series on the right, we had those two blocked off, and we bring our capacitors in series equation up, and now we have 1 over the capacitance equivalent equals 1 over 2.5 microfarad plus 1 over 26.75 microfarad, and we find our capacitor equivalence is equals to 2.29 microfarad. Now that we have this number, as well as this number, this equivalent series, we can make a simplified circuit. Here we have our simplified circuit. As you can see, it is just 3 capacitors in parallel. We have 2.86 microfarad, 7.0 microfarad, and 2.28 microfarad. Now we can use the parallel equation and find our total equivalence. So we have our capacitors in parallel equation. We have this is C1, this is C2, and here is C3. And we have 2.86 microfarad plus 7.0 microfarad plus 2.29 microfarad equals the capacitor equivalence, which is equal to 12.155 microfarad. So finally, for the final answer of the total capacitance of the combination of capacitors as shown is the capacitor equivalence of equal to 12 microfarad.